Thank you, Pawan, for the invitation. It's a really pleasure to be here. I've been following your support group, and as I was just talking to Pawan, I'm really glad to be invited to present here. So I'm going to talk about some new three-dimensional models for reinforced concrete walls that are developed based on some existing models that were 2D, and then we basically extended these models to 3 dimensions. And there's actually 3 different models that are coming to OpenSees really soon. One of them is already there, actually starting this weekend. So very, very new stuff. So before I begin, I want to just acknowledge and thank to all my academic colleagues, John Wallace from UCLA, Guy Rapchel from Bogazici in Turkey, Leonardo Massone from University of Chile, who helped in development and advised in many different ways development of these models, as well as the students in Costa Fullerton who worked in development and validation of these models. You can see their faces over here that had a great time, and I did as well. And those are Nathan, Kamiar, Ross, Carlos, and Ben. So this is the completed project. We're wrapping it up, publishing our papers, and publishing the models as well. So here's a little outline of the presentation. Basically, a little bit of the background, just to put us all on the same page in terms of reinforced concrete walls. And I want to spend a little bit of time talking about these currently available models, which are 2-dimensional models. They were implemented a few years ago. If you're looking into modeling of walls, you're probably aware of these models, but just quickly glance through them. And then we're going to spend most of the time here talking about the 3D models for RC walls that are the new ones, talking about describing those models, validation, when are they going to be released, and then I'm going to show you 2 examples of their application to dynamic analysis of buildings. So just a little bit of the background. Reinforced concrete walls, they're very commonly used worldwide to resist the seismic forces, because they provide large strength and stiffness to the structural system. You can find them as isolated walls, such as this wall over here, or you can find them as a coupled or core walls, such as this picture over here. And given the performance-based design, which is more and more used in design and evaluation of buildings, using the nonlinear models is very common, and having good models for perform these tasks is really, really important. So just, in general, we can kind of classify reinforced concrete walls and their behavior and failure modes according to their aspect ratio. So, roughly, if you have a reinforced concrete wall with height divided by length, which we call aspect ratio, bigger than 3, those walls are primarily flexure dominated. If we have something that we call medium rise walls in between 1.5 and 3 aspect ratio, those are dominated kind of with a combination of flexural and shear deformations. And if we have squat walls, such as this one over here, they are shear dominated. And you can see by the cracking patterns of these walls how here's basically pure shear. Here we can see both horizontal and diagonal cracks. Here we really can't see the cracks, but obviously with such a slender wall like this one, it's a flexure dominated. So that's kind of a big picture. First thing when you look at the wall, that's the first thing you notice, and that can tell you something, what you can expect in terms of behavior of the wall. So let's talk about these existing models just real quick. And these models are implemented in 2005, I believe, in OpenSees. Some of these models were part of my PhD dissertation at UCLA. And then after that, we implemented them in OpenSees. And there's a peer report from 2015 that describes these models. And here, as a part of that effort back in 2015, we implemented the MVLEM model, the shear flexure interaction MVLEM, and then we implemented this 2-dimensional material, which is called fixed strut angle model for reinforced concrete. And we also implemented 2 uniaxial material models, concrete CM and steel MPF. So you can read about all these models in corresponding papers, but the implementation part of it is published in this paper here in Computers and Structures. There is a reference, and as well in this peer report. So, the MVLEM model is basically a 2-dimensional 2-node element. It's kind of like a beam column element, but it's 2-dimensional, and it's primarily for walls because it has this kind of a planar cross section, which you discretize into fibers. So essentially, it's a fiber model. It has these rigid beams at top and bottom. It has a total of 6 degrees of freedom at these 2 nodes, the behavior of these uniaxial fiber elements is really governed by the concrete and steel material models that are uniaxial materials as well. And they're used to behave the flexure, to describe the flexural behavior of this element. And then the shear behavior is uncoupled from the flexural behavior, and it's defined and behaves according to the shear spring, whatever material you use. Here is the wiki page. Back in the day, now the OpenSees is moving to GitHub, but in that time there's wiki pages for these models, so you can read more about them and how to use these models. Here there's some examples as well. So this model was validated because it's a mostly flexure dominated kind of a flexural model, because it has these flexural fibers and the shear spring. So we validated it pretty much mostly against the flexural dominated walls, such as this one, specimen RW2, for example, from Thompson and Wallace. And you can see that it has a pretty good, behaves pretty well in terms of the global force deformation, and also in terms of the strains predicted at the base of the wall. So both global and local behavior were pretty reasonably well predicted. However, when you try to model, say, a medium rise wall that has a significant contribution of shear deformations, and this model may not be the most appropriate one. So here we have three results that are different in the way the shear behavior and that shear spring was modeled. If you use linear elastic shear, you will get something like this, right? Where you basically overestimating the capacity. Then you can say, okay, now, because this particular specimen had significant contribution of shear deformations, maybe I want to use kind of like an elastoplastic shear spring. And then depending on what capacity you put into that spring, you can get these results. And these results on a big kind of global behavior seem quite reasonable, although you can see kind of like artificial behaviors, not really a natural. And the reason is that, again, here, if you look at the shear behavior of these specimens, so this is just the shear deformations versus the lateral load. In the linear elastic case, you're doing, with the model, you're doing something like this, but your actual specimen is experiencing something that looks like this blue line. If you try to do that with other types of the shear hinges, again, you can kind of match reasonably well these shear displacements, but the big problem here is that these shear and flexural behavior are totally uncoupled from one another. So the actual flexural strains now and the local responses will not be predicted very well. So this was kind of a motivation to develop a model that really captures the interaction between shear and flexure in a physical manner, and can predict these type of results without any artificial parameters adding, these different shear behaviors and so forth. So for that reason, we developed this shear flexure interaction version of this model, still a two-dimensional model, but we replaced each uniaxial fiber with a two-dimensional material model for reinforced concrete. And this material model is essentially a 2D plane stress relationship between strain and stress, right? It's like a material model in 2 dimensions. And after we had that, we basically obtained this, what we call the shear flexure interaction MVLEM. That one is also published. There's a wiki page link down here, and it's been used in the past few years by several people. I've been contacted many times, so it's been popular, right? And really, it's here's the benefit of this model, right? Here we can see that for this same wall, that the MVLEM was kind of very sensitive to the different predictions of the different way you model the shear behavior. This particular model captures the interaction between shear and flexure, and in a physical manner. So you can see here in the shear behavior, we can actually obtain the nonlinear shear response, the nonlinear shear hysteresis that is pinched, which is pretty typical for shear behavior, and also the yielding between shear and flexure occurs about the same level of lateral load, and which is also what was observed in the test, which tells us that the model does capture the interaction between shear and flexure. So shear flexural interaction.
Excuse me.
So
sorry. One quick question.
Sure.
The blue lines are the experimental and the red lines are the model. Oh yeah, there is. Sorry.
Yeah, the test is the red, the model is the blue. Just this two-dimensional model for reinforced concrete that was put into the SFI MBLEM is what we call the fixed strut angle model, FSAM, also available in OpenSees, right? Here's the link to the wiki page, and here's the actual reference to the paper. And it's a fairly complex two-dimensional material model for concrete, reinforced concrete. It really has these two fixed struts that have the ability to behave first as uncracked concrete, then the first crack forms, and the second crack forms. So it has like a 3 stages of behavior. And steel is modeled through the basically uniaxial, horizontal, and vertical reinforcement behavior. And on top of that, we have these two shear aggregate interlock, two shear resisting mechanisms across the cracks of concrete, which will be the shear aggregate interlock model, as well as the dowel action, which is in this case modeled just like a linear elastic. So this is the element, or actually the model that was implemented in OpenSees. In the past couple of years, Dr. Orakchel from Bogazici University worked and improved this model quite a bit in terms of modeling of shear aggregate interlock and the dowel action, and extended this model. So we're hoping that in the near future we can implement that one, an improved version of this fixed strut angle model in OpenSees as well. Here's some validation against the panel tests. You can see that the stresses and strains are predicted pretty well with these with this material model. And moving on to the uniaxial concrete material, this is a Cheng and Mander formulation, but OpenSees really at the time didn't have a full formulation implemented. And what's really kind of specific for this material model is that it's very detailed. And as you can see on this conceptual strain stress behavior, it has these transition curves that are smooth, and it also has the ability to model this gradual gap closure when basically concrete gaps are closing, right? So a lot of models don't have that, and they have very abrupt closure, and that can actually affect your results. And we will see later on, I have one example to show you how choice of different material models will actually affect your results. So here as well, additional feature of this model is that if you zoom into the tension side, it has this parabolic tension stiffening versus like linear tension stiffening, for example, concrete O2, right? So it's fairly complex model for uniaxial material model for concrete. And then we implemented it in OpenSees as well. There was a simplified version of that model, which was concrete 07, which is also Cheng and Mander formulation, but simplified. And you can see how the hysteretic rules are kind of improved in this concrete CM formulation. Of course, with that complexity comes numerical efficiency and stability. So it's kind of a trade-off. Sometimes, if you need something where this makes a big difference, then it's available to you. But if you want to model a 40-story tall building, maybe you can get away with the simpler material model. So it's really the matter of choice. And finally, part of this whole background implementation was steel MPF, which is Menegotto Pinto Filippo model. And they're basically, it's the same as steel O2 in a way, but improved. Again, the steel O2, and it has some kind of an anomaly in the sense that if you have a little unloading in your strain history, like a partial unloading, let's say in one time step due to, say, crushing concrete in some other part of the structure, this particular fiber wants to unload, or because of the time history is such that causes this unloading. And actually steel O2 will overshoot this strain, if you keep going forward, and it will behave kind of unrealistically, like you see with this red lines. So the steel MPF, we fixed those problems by adding a lot of history variables to track what's going on with the strain history and to overcome that issue. So that produces a little bit, it produces more realistic behavior. And this is part of the formulation of the model, which is actually this anomaly is acknowledged by Filippo in their papers. And so it's not part of the how steel O2 is implemented, it's actually part of the model formulation. And there's another detail, it's about curvature, this transition curvature from elastic to plastic, how it degrades with cycles in the pre-yielding range. So those are the major differences between the steel MPF and steel O2. Here are some examples. For example, this is the RW2 specimen test versus model using the concrete CM and steel MPF. You can see the results are quite quite reasonable, quite good. But then if we, for example, use different material models, such as concrete '07, you get this kind of different looking line, right? Obviously, due to simplification of concrete material model, the hysteretic shape is not as natural looking. And then if we use, for example, concrete '02, concrete '02 doesn't have that gradual gap closure that concrete CN does. And because of that, you see in this region here, when you're reaching back to zero displacement, your gaps are closing very gradually and then picks up. So you basically have that very, very pinched behavior. So this is just a quick example of how using different material models actually affects predicted hysteretic behavior. So to sum up this part, kind of introductory part, what's currently available are these classes over here. MVLEM, SFI, MVLEM. If you want to do just a two-dimensional analysis, this is the way to go. There's no reason to get anything more complicated than that. Sort of a flexural model, the SFI, the shear flexion interaction model, and these material models here. But if you want to go and model, these models are only 2D, and that's their downside. And if you want to model complex building system where you have interactions between walls and beams, and the walls might not be just two-dimensional, but also it's like a core wall or a T-shaped wall or something like that, then you have a problem because, first of all, because of the two-dimensional formulation, it's simply impossible to model the whole building. And secondly, the connection between these, say, wall element and a beam element, current three-dimensional models, for example, beam column element, doesn't really allow that, right? They are only two-node elements. So a lot of times what we have to do, if we want to do this with current tools in OpenSees, you can, for example, choose to do either displacement-based or force-based element, but you would have to have some kind of embedded beams to connect the center line of your wall element to the beam, right? And that's kind of cumbersome. It's not really a problem or anything like that. It's just cumbersome. And then your model stability and results also depend on the parameters of this embedded beams. So the next part of the presentation is going to show basically work that was motivated by these two shortcomings: the lack of the three-dimensional models for walls and the fact that you use this embedded beam, which makes it just cumbersome. So in the next models I will show, we overcame these issues. So I'm going to switch gears here to these new 3D models. Okay, the three-dimensional models that I'm going to be discussing today, there's going to be 3 of them. 2 of these models are directly derived from the original two-dimensional formulations from the multiple vertical element and SFI MVLEM. So we have something that we're now going to call MVLEM 3D and SFI MVLEM 3D. And then we also added one additional class, which is I call it Quad RC because it's a finite element 4-node type of a model that is really not only for walls, but for any type of reinforced concrete element. You can model diaphragms with that, or anything else that requires kind of area elements, right? So these are the 3 new classes that are coming into OpenSees this year. In fact, the MVLEM 3D is already there, and these other 2 are coming. We're just waiting for papers to be published. MVLEM 3D paper is in print right now. So let's talk about that a little bit. How do we extend the 2D to 3D? Well, conceptually, it was fairly simple. We just basically said, okay, we had 2 nodes. Let's convert this 2-node element into a 4-node element. And in order to do that, we added some internal beams to basically interpolate the deformations and strains in this type of an element. And so that was kind of a step number 1. And then step number 2, we needed to add some out-of-plane stiffness. And the simplest thing for starters to do is basically to add that elastic plane element. So basically like an elastic out-of-plane behavior. This model now, we call this MVLEM 3D. In-plane and out-of-plane behavior are currently uncoupled. Out-of-plane is just elastic. In-plane is this 4-node MVLEM. It's fairly similar to Perform 3D shear wall element. If you are using Perform 3D, you're probably familiar with that element. However, it's an OpenSees. It allows you using better material models. There's no limits in the number of fibers and all the things that are sort of limiting for Perform 3D users. As I mentioned, this paper about this model formulation is currently in print and is basically expected to be out in, I don't know, I would say a couple of weeks. So I would like to draw, if you guys are interested, I can send you a little link to sign up or something like that. We can do that at the end. Every time they publish a paper, you have 50 days. You can download a paper for free. And I can send you a link if you send me your email, and I will send you that link and you can have the paper for free within those first 50 days. So why not? This paper is going to be...
Or you can send me the email link or whatever. I can send it to the whole group. They can.
Okay, great. I have like a little
yeah, I mean,
Google form, right?
Cool.
So I just thought to spread the word, because many times I want to download something and I don't have subscription to it, and then I have to ask friends and stuff like that. So sure, I can forward you that information. So that's that model, and here's the input parameters. I just want to describe them a little bit. So basically, you need to, in order to define this element, you need to define the 4 nodes in the counterclockwise direction. Then you have basically array of thicknesses for each fiber, array of widths for each fiber, array of reinforcing ratios for each fiber, array of concrete tags, steel tags, and the tag for the shear material. This is basically exactly the same input as for the 2-dimensional MVLEM, except you have 4 nodes instead of 2. And then we have this parameter C, which represents the center of rotation. Basically, where is this center of rotation of this element located from the bottom of the element? That used to be an MVLEM to the 2-dimensional. That used to be a parameter you have to put in, but the recommended value is 0.4, and it works really well with that number. So right now I put it into an optional parameter. It's by default is already using 0.4, so you don't have to bother with that. Trying to simplify the input a little bit. Then there's a factor that you can put in to modify the thickness, the out of plane, for the out of plane behavior, if you want to play with the out of plane stiffness. Default number is 0.63 because that gives you 25% of the out of plane moment of inertia. But if you want to use something else, you can do that by modifying this T mod parameter. If you want to use 0.63 to get 0.25 to get 25% of stiffness, then you don't have to do anything. Same thing for the Poisson ratio and density. They're optional parameters with some default values for concrete, and density I just put 0 because people model mass in different ways, so it's possible to add that as well. So that will be the input format for this element. In terms of the shear flexion interaction 3D element, it's essentially the same concept. We transport 2 node to the 4 node, then we basically glued to it this out of plane elastic element. The only difference right now, right, the body of this in plane behavior is shear flexion interaction model, and it ultimately it becomes this SFI MVLEM 3D. This paper is currently in review. Papers take a while to get through review. I submitted it back in September, so hopefully it will be out soon. And as soon as the paper is published, we'll publish the model as well. In terms of input parameters for the SFI MVLEM 3D, very similar to the 2-dimensional version, except you have 4 nodes. You have an array of thicknesses, widths, and material tags. The material tag is basically has to be a tag of the fixed strut angle material model, FSAM. So each of these panels here have to be FSAM. That's the only way to make it work. And same thing for as a 2D model. And these other parameters, just the same as I explained for the MVLEM 3D. We have C, thickness modifier, Poisson ratio, and the density. They are all optional, and they have some logical default values. And finally, we have this quad RC element, which is basically a 4-node finite element type of a model. It has 24 degrees of freedom. They all really do. They all have 24 degrees of freedom in 3 dimensions. And it's a standard 4-node finite element formulation. We just made some adjustments, modifications, so it works with this fixed strut angle model, and also it has elastic out of plane behavior similar to the previous two models, right? So and it's kind of practical finite element type of a model that you can use for three-dimensional analysis of walls or any other area elements made of reinforced concrete. Here's the input parameters, pretty standard. It's again 4 nodes, thickness material tag related to the fixed strut angle model, and the same optional parameters for thickness, density, and Poisson ratio. Again, paper is in review. This paper is actually hopefully will be out sooner. I'm responding to comments right now. I'm supposed to send them back next week. So hopefully, in the next couple of months. So if any of these models or papers are something you guys are interested in, again, I will forward you the little Google spreadsheet where you can put in your just email address, and I'm just gonna send you, these links and information when they become available. And now let's talk a little bit about validation of these models. That was their formulation. We mostly validated the models with the tests from Bayer and Constantin from Switzerland. And they tested these 4 wall specimens that are U-shaped walls, TUA, TUB, TUC, TUD. And as you can see down here, all of these wall specimens were tested in very interesting loading protocol. TUA and TUB had this kind of a spider web shape, very complex, kind of a loading history, so multi-directional loading for these walls. And TUC and TUD, they were going in mostly diagonal loading. Very initial cycles were in the A, B, and CD directions, and then mostly the walls were loaded in diagonal directions. So that was kind of a perfect set of experimental data for us to validate these models, because they are, first of all, non-planar specimens, so they're U-shaped, and they were subjected to the complex multi-directional loading. So it was really, really helpful to have this set of data and validate the models against it. So here's how we build these models, just a little bit of information about that. When we were talking about MVLEM 3D or SFI MVLEM 3D models, we used one element for each flange or web, and each of those elements were discretized in a number of fibers. And you can see how that fiber discretization looked like here. In a cross section, we have confined and unconfined concrete, and we calibrated material models, basically using some procedures that are explained in those papers, but basically trying to match the as tested material behavior for steel coupons or concrete cylinders, right? Of course, we have accounted for confinement as well. When it comes to the finite element model, the quad RC, we actually had a little bit, you have to discretize the wall differently, so it's a little bit more finer discretization, where each of these fibers now became one element, kind of like here, right? So a lot more elements, obviously, in this case. So that would be kind of the geometry of the wall, how it's discretized. We applied the loading at the locations where the loading was applied, and it was kind of interesting to figure out how to apply the actual loading history, because these U-shaped wall specimens were where the twisting was fixed, so it was not twisting, and we had to add some springs to stabilize the model and then apply forces on these locations of the actual actuators. And this thing, again, it's kind of complex. I'm not going to get too many details, but it's explained in these papers. And then here you can see the loading history that was applied in the model, which was red, and the test loading history, which is black. You can see that this is kind of the best we could do to match the two. And I think we were pretty successful in terms of that. So we applied exactly the same loading history as in the test. And here you can see a little video of one of these. I think this is the quad RC model, moving up and down, left and right, and mimicking the behavior that was in the test. Of course, displacements is exaggerated here quite a bit. So that was one little animation. In terms of the analysis times, what's really nice about these models, especially like MVLEM, again, depends what you want to do, but this MVLEM is very, very fast and very stable. Convergence rate with So the way we analyze it, we first start with the standard Newton method, right? And then if it doesn't converge, then we use Newton with initial stiffness. Those are the options that you have in OpenSees, one of the many. And here you can see what was the convergence rate with the current tangent, so with just the original Newton algorithm, and it was almost 100%, right? In terms of the number of times, the number of loading steps where you had to switch back, where you actually successfully converge with the Newton. Analysis time for each of these models was also quite short, about a minute or two. In fact, I think they're even shorter now because I've done some modifications to the element to improve its numerical efficiency. So these numbers are slightly shorter than that. But in any way, it just takes 1 minute maybe to apply about 12,000 steps of analysis with these models. With the SFI MVLEM 3D convergence rate a little lower, slightly, still more than 99%, but analysis time was quite increased due to complexity of this model. And also, as soon as you start converging with the initial tangent, just the efficiency of that solution strategy is much, much lower. So even if, part of this, you see this, for example, 99.7%, you were able to converge with the current tangent, and only 0.3% you need to use initial, and analysis time is 11 minutes. If that 0.3% goes to 0.8, it jumps to 27 minutes. So it's really, they're related, right? So, so much about the convergence rates, and I thought it was kind of interesting to actually compare these numbers and see what they are. This was ran on my office computer, which is, I don't know, it's not like a laptop, it's more powerful than that, but it's also not like supercomputer. So here you can see what performance, what are the properties. Here are some low deformation results for this one particular specimen, TUB. And just from a big picture, looking at it like this, so here we have, it's kind of like a matrix, right? So each row represents one model results. So MVLEM 3D results are these three, SFI MVLEM 3D are these three, and Quad RC are these three. And here we see different loading directions, east-west, north-south, and diagonal. And this is basically a square root sum of squares in terms of the force and displacement. So from a big picture, when I look at it, I would say, well, they're all kind of doing okay, especially when I'm talking about the loading in east-west or north-south direction. That is when we're in the principal direction of this cross-section, right? There's not much difference looking at the load deformation relationship. I can observe that MVLEM 3D kind of has this funny shape here that maybe unloading doesn't match super well. SFI MVLEM does a better job in terms of that. So it's obviously something related to shear behavior, because SFI has kind of couples, shear and flexural, and this one is uncoupled. So this really depends on the shear stiffness you put in there. But, in the other direction also, it's pretty good match, I would say. The major difference that you can see is in diagonal direction between these three models. And if we start from the top, from this flexural model, you can see that it overestimates the strength by almost, I would say, 40% maybe, as this position E over here. So when the wall is pushed towards position E, and better results, but still not, still kind of like considerable overestimation in position F. And the reason for this is that these two models, MVLEM and SFI MVLEM, use plane sections remain plane assumption. So it's kind of like a beam formulation, Bernoulli-Euler assumption. And because of that plane sections remain plane assumption, you simply cannot predict the nonlinear distribution of strains in the wall along the cross section of that wall. We will actually look at those results in a second, and you will see exactly what causes this. So, but that's the major reason, right? When I have this flexural model, I'm overestimating by this much. If I improve this model by introducing the shear flexure interaction and coupling, the results seem slightly better, but still overestimating. And really the only model that I was able to get good results in terms of the capacity in this diagonal direction was this Quad RC model, which is a finite element model that actually is not based on the plane sections remain plane, and it allows nonlinear distribution of strains along the base. So it's really, that's the catch, right? The model formulation. So something to keep in mind. This is true for any plane section model, including Perform 3D or any other model. Here, the same results, low deformation, but for TUC, a little bit different loading protocol, right? Mostly diagonal. And you can see the same problems in terms of, because these was mostly diagonal, we can see that overestimation, except in the quad RC, the finite element model does the best job in terms of diagonal capacity prediction, right? So similar observations, right? Here we're looking at strain predictions. I know that these slides are packed with information, and I'm not sure what the practice is, but I'll be happy to share these slides after the presentation as well. And you can see in terms of the strain predictions, reasonable job, I would say, in terms of predicting tensile and compression strains in both of these elements. And these are strains along the flange over here, along the height, right? Not perfect, but not totally off. I mean, predicting strains in concrete is quite challenging. And also keep in mind that these are really not apples to apples comparison. The models results are obtained here at the center line of these walls, and the test results are shown for the LVDTs that are inside and outside of the walls. So, looking at it that way, the model is, I would say, reasonably accurate in terms of predicting the strains along the height. And here's that plot of the strains along the base of the wall. So here we're looking at the MVLEM 3D model first. So looking at the base of the wall here and the vertical strains, right? And at this particular position C, you can see that even this MVLEM model does a pretty decent job in terms of predicting the neutral axis depth, the magnitude of these strains, and the distribution. And this is because we're loading it in the principal direction, right? As soon as I push this model in diagonal direction, the strains distributions in the test are becoming quite nonlinear, especially as we progress and have more and more displacement demand. And the model just simply, by the definition, cannot capture that nonlinear strain distribution, and instead it does the straight line, right? That's all it can do. And this is the reason, the neutral axis depth is not predicted correctly. You have much more tension strains, therefore you have much more tension capacity, and that's why we're overestimating the capacity in those diagonal directions. Similarly for the other diagonal direction over here. Similar problem, a little bit better predictions for the shear flexion interaction model. Again, these results make a lot of sense too, because this model now has nonlinear shear deformations. That means that some of the flexural strains will unload and shear deformations will increase. So similar trend of strains, but the magnitudes are smaller because, as I said, flexure unloads, shear increases. And again, straight line cannot predict nonlinear, strain deformations, so strain distributions. So again, another reason we have that discrepancy. The only model that can do this reasonably well is this quad RC that does, again, not perfect prediction, but it is able to capture this nonlinearity in strains at the base. And kind of interesting, really, all these global results are really affected by the local responses. Another very interesting thing, by looking at the global, by looking at the local results, we were able to address here is to really compare the strains, the compression or tension strains, and the resulting shear stress, right? So basically, we're looking if I have compression in one of the fibers, that fiber will be able to resist a lot of shear, right? Because the concrete cracks are closed, and you can, resist shear. But if you put a tension, then you can resist much less shear at that particular fiber. And these results, now we're going to kind of talk about it a little bit, but they exactly show that the model is capable of capturing this behavior, which is intuitively something we expect. And that's exactly what we see here, right? If you pay attention to any of these results, compression is on this side down here. This shear flexion interaction model captures compression stresses concentrated at those boundaries. The same thing here, if I push it to position E, compression is concentrated here and a tiny little bit here. all the shear stresses are also concentrated here and here. And same conclusion in this direction. All the shear stresses are really concentrated at this boundary because that's the boundary that is in compression. Everything else is in tension in terms of the cross section. So this is really interesting and important, actually, especially when if you are someone who is doing analysis of the core wall buildings or any kind of building that has a sort of a C-shape or U-shaped wall like this under multi-directional loading. Because what this really means is that all shear demand is resisted only at those boundaries that are in compression, and the tension side of the wall, it's really not resisting much shear. So models that we currently use for design, like Perform 3D, for example, or even the MVLEM, the uncoupled one, cannot do this, right? They usually assume that the shear is uniformly distributed, the shear demand, right? The shear force is uniformly distributed or in some other way, but in reality, it's really not like that. And then you can ask yourself, well, am I actually predicting shear demands accurately when I'm designing this wall or not? Well, this model hopefully will help make one step forward and improve these predictions. A little bit of the contributions of shear versus flexural deformations to the total displacement, right? So the total deformation equals flexural plus shear, right? So we can kind of, in our models, we can uncouple these two and compare them. They did the same thing with the test results. And here you can see that for SFI and VLEM 3D, in position A and E, it's almost perfect match, but then in the other positions, I'm sorry, A, B, and E, F, right, it's pretty good match. In the C, D, and E, F, now these are flanges versus web, so it's kind of like, essentially in the web, we're doing pretty good job, in flanges, not as good, right? But still capturing the overall trend, I would say reasonably in terms of what is the contribution of flexural deformations to the total. So it's about, say, 80%, right? If we use the other model, the quad RC, situation kind of flips, and then we're doing better job in the flanges and maybe not as good in the web. But both of these models, I mean, capturing nonlinear shear, especially in the C-shaped wall under multi-directional loading, obviously, is not the simplest task. But I would say these models do reasonably well in terms of that in both cases. Cracking patterns. We're actually able to, because there are cracks associated in this FSAM material model that we use, so we're able to process cracks, their orientations, and their essentially evolution throughout the loading history. Here you can see just a couple of cycles at the beginning when these cracks form in the model. And it's kind of interesting to see that, how they are developing and forming. And then what we did after we kind of observed these cracks, then we compared them with the test specimens. And again, the distribution, the orientation of cracks seems pretty reasonable, which tells us that the way stressors and strains are flowing through this model and the specimen are, I guess, in a reasonable agreement. And one thing, what I kind of noticed when I was post-processing these results is that, especially when you increase the scale factor of these, videos, they all have very different deform shape, which is exactly what you would expect based on their formulation, right? The MVLEM model is pretty much just a flexural model. And you can kind of see there's a plastic hinge forming at the base, and the rest of the wall is elastic, and it's almost like a rigid body, right? In the shear flexion interaction model, I can see that I do have some flexural hinge, but I also have some shear deformations at some point over the height. And this model has both the quad RC, but it also has this breathing mode because it allows this stretching. So kind of interesting, and really like all these models are different in a way conceptually. So when you analyzing your walls or buildings, we should be aware of these things, and I would say pick the right weapon when you're trying to solve your problem. Okay. In summary, here we have 3 conceptually different 3D models that are implemented in OpenSees and will be public sometime this year, right? We have this flexural model, we have the SFI, shear flexion interaction model, and we have this finite element-based model. They're all three-dimensional, so they can be used modeling of real building and building systems, right? So we're very excited that, you know, expanding considerably OpenSees capabilities in terms of modeling of wall buildings, right? In terms of the implementation of these models, as I mentioned, the MVLEM 3D was already available since I believe this week. Is implemented it's in the source code. Here is it's the pull request 546, but I believe it will be in the next build of OpenSees. So it's not in 3.2.2, that's current one. It will be next one. But if you want to download and compile it on your own computer, you can do that, right? The other two, the shear flexion interaction and the quad RC, should come around. I'm expecting fall and summer based on how the paper reviews are going. And again, if you have any questions about these models, if you're interested to kind of follow them, and if you want to receive, you know, papers when they're free, right, in the next 50 days, and if you have any questions, feel free to contact me, and I will share this Google form with Pavan, and he can then distribute it against participants here, so you guys can sign up for any updates about these models as well. And quickly, I want to go through some examples over here. Here's the first example of how we use these models to do the dynamic analysis. Like the first example is the 4-story reinforced concrete building tested at E-Defense Shake Table, I believe back in 2010 or something like that. So it's been a while, but this specimen is by now, I think, analyzed a lot and pretty well known. So we did model the whole building. I'm going to focus here on more the wall direction. The way we model this building, we actually have a little pre-processing tool that is called Convert ETABS to OpenSees. So we make our models in ETABS, and we have like a single click type of a tool that converts it in OpenSees. And you can see different types of elements that we are using here. We're using the MVLEM 3D for the walls, and we use nonlinear beam and columns, and the elastic shell elements for the slab. So here's that tool. If you guys are interested, that's another thing that's totally a different topic that I'm not going to talk about right now very much. But there is a website you can visit. Take a look. There's a video there that basically shows how this process works of converting model from ETABS to OpenSees, and then it's really a single click type of an analysis, and it's really easy to use. And I was able to model a lot of different buildings using this tool. So visit the website if you're interested. It's something you think might be helpful for your research. This is the model in ETABS now, so it's kind of silly, right? We're building models in ETABS, we're doing everything there, and then we just convert them to OpenSees. But given the complexity of these problems, that was one way to do it. So we put the masses, we put the gravity loads over there, we define all the material properties for concrete and steel in these spreadsheets in Excel, which are pretty kind of well formatted, and it's pretty easy to use with them. And what's nice, you can also use the functionality of Excel to write formulas and stuff like that, but it's also very practical because you just define all the input parameters in a really nice looking spreadsheet. And then we also have a little macro tool that this software is providing, that you can define cross sections of different fibers. And the same thing for the wall elements, right? This is our MVLEM 3D. So we define all these parameters. Here is how we discretize the cross section. So we used a little bit more fibers at the boundary because we expect and we're hoping to capture the neutral axis as accurate as possible. And then in the web, we use a little bit larger fibers. So we define all these in the spreadsheets, and then we click, in that convert ETABS to OpenSees software. We run analysis, and here's a visualization of that building under, I believe, let's say 100% Kobe earthquake. And there are some tools you can use to post-process and create these videos. And what you're currently seeing is the flexural strains in the walls, how they change throughout the analysis. Looking at the results here, actually in reasonable agreement with the overall load displacement behavior recorded during the test. We have, this is a sequence of ground motions. First, they applied 25% of Kobe, then 50%, and 100%. And we can see that throughout that sequence, the MVLEM 3D, right, is doing pretty good job in terms of the overall behavior. We also looked at the history of the roof drift, also pretty reasonably well predicted. So the model does a nice job for dynamic analysis as well. This is some kind of a validation. Here are some local results, which are a little bit more challenging to capture, especially after you start having degradation in the wall and different failure modes. But I'm pretty happy with the strains. At least this is a strain prediction at one of the wall boundaries throughout these 3 ground motions. And here you can see the overall maximum strain profiles. We can tell that the model is predicting the height or sort of the plastic hinge length pretty well, the height over which you capture these nonlinear strains. And we look at a strain history if you're not too picky, and you have to kind of be reasonable here. These are really dynamic strains. So in some cases, they're pretty good predicted, but this particular wall actually had a kind of a shear failure at the base, and that's probably the reason we had larger earthquakes. We don't have it was shear sliding, so we don't have that good a prediction of the flexural strains in the larger earthquakes. And one more local result is rotations of these beams that are adjacent to the wall. This is now important because we have these embedded beams in the model formulation that allows you to directly connect beams to the wall, so you don't have to do any kind of additional artificial elements. And these rotations are again pretty reasonably predicted, which tells me that the whole connection between the wall and the beam is also probably the way it's modeled with the MVLEM 3D is probably reasonable, right? So those are results for this particular dynamic analysis of building. And then I have one quick, really high level example is this 40-story building, reinforced concrete core wall building. It's sort of famous building because it's an archetype that's used for this Task 12 report back in 2011. So it's not a real building, but it has all components of the real building. It's a tall building, typical core wall with core walls and coupling beams. Here you can see the plan view and elevation of this. And this is how we modeled it. Again, we modeled it in ETABS and converted it with this software into OpenSees. We used fairly standard approach. These wall elements were modeled with the MVLEM 3D. And the coupling beams were modeled using just elastic and then shear hinge in the middle. That's kind of a standard practice when it comes to tall buildings analysis. Shear hinge in the middle has some backbone curves that's validated and against the tests. So we ran this particular building model using a lot of ground motions at 3 different scaling factors. And we obtained a lot of results. And this is actually part of another study that's looking into losses of these tall buildings. So, here you can see medians and standard deviations of, I think it was about 20 ground motions in each of the suites. So obviously the model, the MVML 3D, is working. Even in a big model like this, it took about, I believe, about 1 day for 1 ground motion, which is not too bad. And here you can see a little video of this building dancing here to the left. So in summary, there's 3 new models, right? One of them is already available. 2 of them are coming. They have different capabilities. They're 3-dimensional models. They're 4-node models. And you can very easily connect these models with other parts of the elements in the building. And they're validated, they're documented, papers are also coming out, right? So if you guys are interested in any of this stuff, again, there's a Google form here that I will share. And there is also this convert ETABS to OpenSees software. If you're interested in something like that, take a look at the ceostructural.com. I believe I discussed this shortly with Pavan before. I will be happy to come back and give another talk about this converter tool sometime down the road, maybe in a couple of months. That's all I have for now. So I'll be happy to answer any questions.
Awesome. Thanks a lot, Christian. It was like an intense one, like with a lot of new elements, and good to know that OpenSees is expanding like a lot in this area.
Yeah.
So that's awesome. And like, guys, anyone with questions, please feel free to ask. A lot of people I know who are working on walls are here, so maybe they can.
I have a question. Hi, Sir Christian. It's very good to know that the model is already available. I was waiting for it actually. Um, so I have a couple of questions, but one of these is, what do you suggest for how tall or how, yeah, how tall should be the element? I'm thinking on localization problems. So what do you suggest for the tall of the element, or maybe the aspect ratio of the elements for a normal wall in a building?
So let me try to go back maybe to this slide over here. Well, here, okay, here we kind of overdid it in a way that we matched the size of the elements with the measurements in these tests. So if I'm supposed to model the actual building, I probably wouldn't use these small elements. If this is like a industry project or practical project, usually we have some expressions to estimate the plastic hinge length of these walls, and then you want your element should be at least as the plastic hinge length, right? Shouldn't be more than that. And then you can use a couple of elements over the height of the plastic hinge if you like. It really all depends on the size of the model, the configuration, a lot of things, but that's general consideration. Try to estimate a plastic hinge length and then go from there.
Okay. Another question regarding to the validation that you did for by using the test in Japan. Did you made a calibration for your model? Because the match looks very good even for the linear range. So I don't know if you perform a calibration previously or something like this.
We didn't do a lot of. I'm trying to find that. We didn't do a lot. We just use a standard approach, right? The model is fairly complex, so it has all the nonlinear elements. So that part of it, there's nothing much you can calibrate there except the material itself. We had the parameters, we had the material strengths and all that information. So we did it the best we could in terms of calibrating our materials. And so there's not a lot of kind of bogus parameters that you need to calibrate. One thing that made some difference was because this is now a 3D building, right? So all the elements interact. So the stiffness of the slab actually will make some differences. So we're using, if I remember correctly, quite small out of plane stiffness and like cracked shear stiffness. So we did run some sensitivity in terms of that parameter. In terms of the actual wall element, no, again, it all comes down to the materials. So that was pretty, just based on the test and confinement that we had. And the shear stiffness is, I believe, standard, like half of the G, like 0.5 G for cracked shear. It was just the linear elastic shear. So we didn't do that much. And one parameter definitely play with was stiffness of the slab to observe that sensitivity. But other than that, no, not really.
Okay, thanks.
Any other questions, guys?
Hi, this is Nader from Turkey. Do you hear me? Hi.
Yeah.
Thank you. At the beginning, thank you for the presentation. I have a question about the material. You're still using concrete CM and steel MPF, I think, or maybe it's
so
different.
there's just a lot of details here that didn't mention that. So for these bigger models, we're using concrete O2. So for all the building examples.
Good, because as I think the 2D SFI, it only works with the concrete CM.
Right. That's another thing we need to
good.
add to OpenSees. On the side, we modified that fixed strut angle model so it works with other material models, especially concrete O2, because that's like the most stable one. So you would have to do that modification to make it work. And good thing you reminded me. That's something that if you guys want to use these models, we have to implement that as well. So we use Concrete O2 for most of these analysis.
So the new 3D models are working with other concrete and
Yes.
steel.
Yeah.
Okay, great.
Not all of them. There is I think Concrete O2, Concrete O1, and a couple of those, right?
They are the common ones.
Yeah, there's some modifications you need to do when it comes to this actual formulation. Oh, where was that? When it comes to cracking criteria, how these cracks form depends on the uniaxial material models and how they crack. And so depending how the cracking and the tension behavior is defined in uniaxial material model, and every model may be a little different, you have to kind of make some modifications to make it work. But I do plan to release the one that at least works with the Concrete O2, because that's like the one that most of the people use.
Yes. Okay, thank you. Maybe another question about the quad RC. Could you have any sense about the mesh size you used for when modeling?
The mesh size was, obviously these slides are not exact. Like this slide is exact mesh size for the MVLEM and for the SFI. For the mesh, quad RC is more conceptual, but the elements were actually, you can see it on this video over here. And so we used that. This is fairly large. We have another model with smaller mesh size, but it wasn't, let's say the smaller size we used was half of this. So elements will be half of the size.
Okay. Thank you. Thank you very much.
Any other questions?
I have a question. I'm Hadi. I was wondering, is it possible to model punching effect to get the punching in slabs using these elements?
Punching, like punching through slab?
Yes, exactly.
Yeah.
Because when we consider the element same as the wall, just the loading protocol, but the out of plane moment that it is applied is the same as the one of the example that you showed us. I think it was Dr. Bayer's example. I think all this how to say, the experiment were the same as, if you can consider same as wall as a slab. Is it possible to get pinching, all the flexural shear failure?
Oh, pinching. Okay. So I thought you said punching, which is like punching.
Yeah, punching failure and all the pinching effect, pinching, shear, and flexure failure. Punching, yeah. I need punching in slabs.
These elements have a linear elastic out of plane behavior, so unfortunately you cannot capture any punching. You would have to find some element that has non-linear through through thickness kind of a behavior, right? To get the punching. So these elements are not. It's not for that.
Is there any such element that it can help me to model a slab, such as composite?
Maybe there's some kind of a. Is it a 2D problem or a 3D problem?
3D and cyclic.
So for punching failure through, like a punching through the slab, I think you would have to use some kind of a brick elements or something like that. Maybe there's some easier way to do it. If it depends, there's many levels of modeling. Like if you want to make a really detailed finite element model, like Abacus or something, then you would have to find maybe like a cubic element with concrete. I'm not even sure that's available in OpenSees currently. But there's other simpler models with some maybe more macroscopic elements too.
Thank you so much.
These elements are not for the cross thickness kind of a failure.
So I had a similar question, like on this lines I was about to ask, like when you said 3D elements, like all these are 3D elements, right? How different are these?
They
from,
are
like,
3D.
Like my question was like, traditional 3D, which we assume like the continuum models and stuff, right? Like in Abacus and stuff. How different are these from that? Like
These models are not as detailed.
Yeah.
These two, the MVLEM and the SFI MVLEM 3D, they're macroscopic models. So they're formulated based on some assumptions, right? Such as, for example, plane sections remain plane, right?
Yeah.
We have these beams on top and bottom that are rigid. And so when I say 3D models, I mean they can be put into a three-dimensional model. You can model the full 3D building with it. But what's non-linear in models is really their in-plane behavior. The out-of-plane is just linear elastic. So they're not volume elements. They're still planar elements, but in 3 dimensions.
So still like traditionally OpenSees is good for the global responses, right? We traditionally OpenSees is better at modeling the global responses of the structures, not like the cracking and like the spalling of concrete and stuff like that, because it's like a macroscopic element, as you said. But these are able to address some of those issues, but not all of those, right? Like that's my understanding.
Mm-hmm. Well, these models provide local responses as well. Like I showed here, we modeled strains and
cracking patterns,
nonlinear shear deformations, cracks. So those are all local responses. I think that's as local as it gets, but it depends what you need to do, right? These are macro models, but they have a capability to do a pretty good job in terms of modeling local responses.
Cool.
But if you want to model something Abacus type, I believe like there are some elements.
Or something.
Yeah, bond slip or something like that.
Yeah.
Then there could be some other elements in OpenSees that are available for that. I don't think OpenSees is only macro models. I think it has many different models there.
Okay.
You just have to find the right one. Just a side note, you can model bond slip using macro models as well. You can put springs that have bond slip beam and stuff like that, right?
Yeah. Any other questions, guys?
Hi,
Hello. Hi, Professor. I'm a student from University of Auckland, and I wonder if this SFI MVLE 3D model can be used for the shear wall with inclined brace.
Inclined brace. I'm not sure how that really.
The inclined brace means just like an X brace or something like that.
Because is it reinforced concrete wall or?
Yeah, a reinforced concrete wall with inclined brace.
Oh, you mean diagonal reinforcement in it?
Yeah.
Oh, okay.
Sorry, yeah, just like this.
It's kind of an unusual configuration. I believe there needs to be some extension to this material model in order to do that. This one over here. It's possible. Currently this reinforcement is only horizontal and vertical, but it's very simple to sort of modify it to add an angle to it, and then I believe that would be that will enable that type of modeling.
Okay.
But currently no. So currently the reinforcement is only vertical and horizontal.
Okay. Because I saw there are 4 nodes on the elements. Yeah, I think maybe
you could try to kind of combine, that element with some braces or something, but I don't know. I never tried to do that.
Okay, thank you very much. Yeah.
It's certainly something I would give it a shot. It's not that difficult, and I do know that some people trying to model coupling beams like that have diagonal reinforcement, and they're somewhat successful. So.
Okay. Yeah. Thank you very much.
Any other questions?
Hi, I'm Faisal.
Hi.
Do you guys hear me?
Yeah.
Yes.
Professor, do you? Okay. I have a question. How can we model? What's command for plotting? Do you have any command for plotting these model?
Plotting?
Like, yeah,
You mean
plotting.
like post-processing the results?
Yeah, post processing. Yeah.
I just use MATLAB. Whenever it comes to processing stuff like this, like load deformation, any type of a XY plot, I just use MATLAB. You
No,
know,
plotting of these elements,
you mean this type of stuff?
graphical. These are graphs, not the graphical representation, just like you show the core wall.
Like this one over here, for example.
Yeah, like this one.
Okay. This is actually made in software. It's called ParaView.
ParaView. Yeah.
Yeah, it's a free software, and it takes a little bit of time to figure out how it works, but everything does, right? But it's pretty. The way it works, for every frame, you have to have a different text file, and then you just have a lot of text files, and they all connect into a video. It's certainly
Actually,
possible.
some
So that's
models
the one
were
that.
like some models were two node. Some walls were two node. I saw, and so how they are represented in 3D in as plain wall.
Can you refer to a particular slide? I'm not sure if I understand the question. Like I'm showing this, or
if you go MLVM, I saw it was just two noded wall
oh,
in the
well, this is the old one. You're talking about the two node one. For example, this one.
yes,
That's the two.
this one. So it is two node, but graphically they are represented as plain. Yeah.
So none of these are the old two-dimensional models that we later on expanded to the 3D models, and the 3D models are all with the 4 nodes, and those are the ones that I was showing. So I didn't show any of the 2D model video.
So the four noded model, those four noded model, they can be output. They can be represented in ParaView by
Yes.
some output. Okay.
Mm-hmm.
And can we? My second question: can we do retrofitting? Can we represent retrofitting in these walls like FRP? Can we represent FRP in it?
Uh, I I would say that yes. I've never really looked into and tried to do that, but in design, I mean, if you add FRP, you would sort of increase the shear strength or something like that. So by modifying the parameters of these models to kind of do the same thing, I'm pretty sure you could achieve that. Yeah. There's no particular parameter that you put in for FRP, but you would have to find a way to modify the material properties or any other input parameters to, mimic the effect of the FRP. But it's certainly possible. I'm pretty sure that's what engineers do in design as well. I mean, there is no like FRP material or something like that.
And finally, are there any specific recorder associated with these elements, or
Yeah, that's a
they
good
are just?
question, and it's just a lot of details here. There are recorders. Let me show you I believe. See, I forgot to put that in here. I will send you this as well. There is this basically repository here that is temporary, kind of a temporary user manual until I've also set a pull request and they accepted it for the user documentation, but it takes time to build the actual HTML pages. So in the meantime, I will share this as well. And I don't see why I don't see the chat here. Let me see if I can, oh, there it is. So let me drop this link in chat. You guys can save it. So here's the user documentation. User right, that's that one. And then basically, I've seen a couple people already made their own forks of this, but you have a description. Here's the input parameters. Here are the recorders that you can do, right? You can have global forces, curvature, shear deformations, strains, stresses in fibers, and stuff like that. So that's available there. And also, here's basically the same examples with a little video of this wall moving in all these directions and results. And here is the reference to the paper. Paper is, again, as I mentioned, in print right now. So there are recorders, which are these over here. Here's that Google Forms. If you guys want to sign up for updates, if you want me, I can send you a link to the paper when it comes out. This one or any other, really, in the future. So there's another one. I just dropped the link over there. So
I can send this to the people in this section too.
Sure. I'll forward this to you as well.
Thank you.
And we have one more question on the chat. It is like, could you, from Mustafa, could you please explain a bit more on how SFI MVLEM 3D elements capture the out of plane performance or behavior, particularly how the macro fibers or panels capture the out of plane performance?
So out of plane was not really kind of a major goal here we're trying to address. We just added the out of plane, elastic out of plane, right? It's an elastic plate. That's it. There is no, you cannot capture like out of plane instability or anything like that. It's certainly something we're trying to improve and add the functionality to it in the future. But currently it's just elastic out of plane behavior, right? And it's uncoupled from the panels, so it's kind of its own thing, right? They're just kind of two springs in parallel, right? The in plane and out of plane.
Hello. Hey, thank you very much for the presentation. You kind of answered it, so I didn't stress on it. So thank you very much. Cheers.
Okay.
Cheers. Thank you.
And any other questions?
Hi, Professor. I have another question. Have you compared the performance of these 2D models and the 3D models for MVLEM and SFI, these two elements?
2D versus 3D?
Yeah, in plane, of their in plane performance.
Oh, it's identical. It's exactly the same. That's the first thing we did when we did this. When we go from 2D to 3D, then from 2-node to 4-node, the first thing we did, we make sure that we get exactly the same results.
Okay, so the when comparing the cyclical force displacement on the curve, the displacement of the point L of this 3D is the same as the J point in the 2D. You mean?
The L and J, no. So the J would correspond to the middle here, which it doesn't have a node. This guy.
Yeah.
Right?
So how to catch the displacement of this point?
So you could put like a recorder or something. I forgot what the student actually did, but we modeled probably with a couple of elements. These two nodes, the L, K and L, and I and J, they have identical. There's basically a geometric transformation that connects these two. So the element is kind of rigid in this direction. You can't really deform it that way. So they pretty much move the same.
Yeah. Okay. Thank you. Thank you very much.
Any other questions? A lot of questions.
That's good. I'm glad.
Yeah. I have one, basic one. Like I tried to use concrete CM and steel MPF before, and I had like a lot of convergences, like a lot.
Hmm.
Like so, I switched back to concrete O2, especially when I'm pushing like something to failure kind of a thing, like or like cyclic loading. I was having severe convergence issues. I'm using the Python version. I don't know if that is the case for that or Pickle.
Concrete, concrete CM, I can see that, right? Depends how big your model is, but steel MPF really shouldn't give you any convergence. I modeled, in fact, this whole tall building has steel MPF in it, so
maybe together. So I don't know the convergence is from which component, but yeah.
I believe it's because of concrete CM, because it's a very complex model. It's I think the source code has like 1,000 lines just of the different rules and stuff, different hysteretic rules. So it's fairly complex. But usually, what I've seen people use concrete CM is to model more like a local behavior. If you really want to capture that gap closure on some loading reloading, that's the real benefit of it. The global sense, like, yeah, the one thing you won't be capturing if you use concrete O2 is that pinching. You can get like overly pinched behavior because in the concrete O2, in the concrete O2, the gap closes abruptly, and that's why you have this really, really highly pinched.
Yeah.
But if you don't have a problem with that, everything else is okay, more or less, right?
You can get away with that pinch with concrete 07, right? Again.
Yeah, concrete 07, again, here's with the concrete 07, it's kind of the other way.
Okay.
So
because
maybe there's a way to manipulate or calibrate a little better or something like that.
Because I do get one that high initial stiffness thing which you are showing in concrete 02, so that's why I was asking. Okay.
Yeah, concrete 02 is issue, and you don't have a control over the initial module of elasticity, right?
Yes.
And if you have a high strength concrete, then that drops a lot because that parabolic curve is. But yeah, so it's like someone could implement concrete 02 version with the stiffness. That'll be helpful. Initial stiffness, which would be a pretty easy thing to do actually.
Thank you, Chris. Okay, then, looks like no more questions, so we will wrap it up. And I know it's already 30 minutes past the scheduled time, so.
I didn't believe you, but there is a very good discussion.
Yeah, I told you, right? Like usually this session extends.
No, this is great.
Hopefully, about the SAP one, I'll contact you again in some time for that. Like,
sure.
And that would be interesting too, and that's gonna help a lot of people too, I guess.
That little project with this PTABs to OpenSees, it's also almost done, and I'm expecting to have like a trial maybe in April, so next month. So we can, I can come back in a couple of months and talk about that only.